This is Project 2, Roll Transfer Machine from MEMS 1029. I'm Nate Bonacci, and I did the bearings.
I'm Jack Smith, and I did the gears.
I'm George Johnson, I did the lead screw and the motor.
Our team set out to design a machine that could transport industrial rolls of paper from the manufacturing line to a forklift through a 90-degree rotation. With a budget of 45 seconds to transfer the roll and 45 seconds to return to the starting position, we focused on designing the gear train, the lead screw, and the bearings to mount the shaft. Our selection of individual parts was guided by a minimization of both cost and power required from the motor to run the machine. This machine was designed to maintain a factor of safety greater than 2 with an expected life of over 10 years. Our design did not investigate the failure of the cradle shaft and arms, the bolted joints for the pillow blocks, and the structures supporting the bearings. The assumptions we used throughout our analysis can be seen here.
The figures above show a front and side view of our design and the general motion of the system. Working in unison, the lead screw, gear train, bearings are able to rotate the cradle 90 degrees. To analyze how much torque is needed to rotate the roll of paper, the worst case scenario is considered. The instant the roll is lifted from rest, it induces the largest torque in the system. Calculating its weight and distance from the rotating shaft, the maximum torque was found to be 3,870.58 Newton meters. This value can be used to analyze the three facets of our design. The function of the lead screw is to provide a necessary amount of torque to the crank arm. Since the crank arm attaches to the pinion, it requires a constant torque. The motor rotates the lead screw such that the nut attached to the crank arm translates in the direction indicated. Also, the motor and lead screw pivot together behind the motor. This allows the rigidity of the crank arm to be accounted for in its rotation. The layout of this portion of the mechanism let us assume that the start and end position of the crank arm are symmetrical about the y-axis. Therefore, the lead screw and motor will begin and end in the same horizontal orientation. Also, a length of 0.5 meters was selected for the crank arm. Since we know that the cradle needs to rotate 90 degrees in the allotted 45 seconds, we know the larger gear has to have a rotational speed of 2 degrees per second in the shown direction. Additionally, it has to transmit the max torque to the shaft. By working backwards and using a gear ratio with 97% efficiency, we're able to find the torque that needs to be exerted on the pinion by the crank arm and the speed of the pinion. Additionally, the pinion will rotate a total of 135 degrees through one rotation of the cradle. It is important to note that the pinion is driving the larger gear, exerting a large force to achieve the desired torque that will need to be supported by the bearings. To maintain equilibrium, bearings were strategically placed along the rotating shaft on the outside of the cradle to support the forces from the gears and the weight of the paper roll. While in the maximum torque position, the gravitational force of the roll is distributed equally amongst the three arms it sits on.
Our technical analysis began with analyzing the bearings. To understand the load of the bearings, we first analyzed the loading on the shaft in the maximum torque position. The loading force is comprised of gravitational forces from the cradle shaft, 6 arms, and paper roll. The torque on the shaft due to loading is only comprised of the gravitational force from the roll and the 3 arms supporting the roll after the mechanism is activated. Using our assumptions, we calculated the max force and max torque as seen on the slide. To calculate the load on the bearings, we modeled the shaft as a simply supported beam. As previously mentioned, the maximum torque position disperses the weight of the roll amongst the 3 arms. A second model was needed to consider the tangential force placed on the shaft from the gear. Due to the bearing providing forces in more than one direction, we used Pythagorean's theorem to find the total force magnitude. A Python script was utilized to help iteration with various gear forces. With the load of each bearing known, we then analyzed the static failure and its factor of safety. In choosing bearings, the high radial load and non-existent thrust load led us to select roller bearings. Using the equation on the slide and the specs from our selected bearing, the factor of safety for each bearing is well above the threshold of 2. Next, we analyzed bearing life to ensure it would meet the requirements of the required 312,000 revolutions. To meet the factor of safety requirements, we analyzed the bearing to a 99.6% reliability, which resulted in a 99.2% system reliability. Using the dynamic load value of our bearing and the calculated life of each bearing was well over 8 times the amount we needed. The same Python script was also used to help iterate required static and dynamic load values needed to aid bearing selection.
Next, we'll talk about the process of choosing the gears. 3 main factors had to be considered during this process. First was the gear ratio, which will affect the speed and torque transfer. Next is the size of the gear, which directly impacts the lead screw displacement and the tangential forces between the gears. Finally, the strength of the gear, where the tooth stress is analyzed. The final gears chosen for the system had a module of 10 millimeters and had 30 and 45 teeth respectively. Our setup utilizes the pinion being connected to the crank arm, creating a gear ratio setup that allows for better torque transfer to the rotating system. A large number of teeth had to be chosen to limit the angular displacement through one rotation. Additionally, the gear connecting to the rotating shaft had to apply a large torque to rotate the paper roll. This torque is created by the tangential forces between the gears shown in the free body diagram. In order for this force to be minimized, and thus the reaction force in the bearings to not reach a failing level, the diameter of the gear had to be large as well. This led to the conclusion of finding gears with a large module. The primary failure mode of meshing gears is tooth failure. High forces need to be applied to individual teeth to create torque and motion of a gear. In this case, 3 iterations were run to find an acceptable gear size. Both 1 and 5 module gears with their desired gear ratio ended with factors of safety less than 2. By increasing to a module of 10, however, the tangential force, WT, decreased, while denominator terms of face width, F, and module M increased. This led to the pinion and gear having a factor of safety due to Lewis bending equation of 5.78 and 6.44 respectively.
Now we'll discuss the power screw analysis. This portion is made up of 3 parts: geometry, thread failure, and motor power. To fully understand the motion of the lead screw throughout the machine's activation period, we looked at the beginning, middle, and end of the process. We knew that the pinion attached to the crank arm rotates at pi over 60 radians. Using this, we determined that the angle between the lead screw and the crank arm at the beginning is 22.5 degrees and that it is the same at the end. Therefore, we calculated that the necessary force of the lead screw is 13,902.85 newtons at both of these points. To analyze the force of the lead screw at the midpoint, we used the known length of the crank arm, 0.5 meters, and the angle, 22.5 degrees, to determine that the pivot angle, phi, equals 19.17 degrees. Knowing this, we calculated that the force was less than it was at the start and the end, so the larger force is selected. Thus, the lead force is equal to 13,902.85 newtons. To ensure the structural integrity of the lead screw, adequate dimensions needed to be selected. A factor of safety greater than 2 provides a reliable assurance that the screw will not fail. Also, steel was chosen as material for the screw and nut due to its strength, cost, and material properties. The allowable axial stress was set to be half the tabulated maximum axial stress for a class 4.6 screw. The equation was then rearranged to find the minimum minor diameter, which was used to select the rest of the dimensions. The chosen major diameter is 16 millimeters, mean diameter is 14.5 millimeters, and pitch is 3 millimeters. We then used these dimensions in the bearing stress equation to determine the number of threads required, which is 1. The next step was to verify that these dimensions allowed the power screw to be self-locking, which ended up being true. Since steel was selected for the screw and nut, the coefficients of friction are listed on the slide. The torques to raise and lower the load, as well as the collar friction, were calculated. Then the total torque was found by summing the torque to raise the load and collar torque. The efficiency was also determined to be in the standard range for power screws. To find the power, we needed the angular velocity of the screw. This was found by taking the known angular velocity of the pinion and multiplying it by the length of the crank arm, 0.5 meters. This yielded the linear velocity of the crank arm. Knowing this, we could use the equation in the book to find the angular velocity of the screw. Therefore, since we knew the angular velocity and torque, we could find the power supplied by the motor, 2,784.27 watts.
Through our design, we focused on minimizing cost. A large cost saving point was deciding between smaller gears and larger bearings, or vice versa. Smaller gears required larger bearings, which increased price significantly, but smaller gears did not meet the safety requirements. When looking for bearing housings, several retailers offered pillow blocks with bearings already inserted. We chose to use separate bearings and housings to reduce the cost, but we were ultimately unable to find pillow blocks large enough to fit these bearings on commercial retailer sites. The estimated cost for each pillow block came out to be about $45 after looking at the linear nature of cost versus inner diameter of the housings on McMaster-Carr.
To minimize the power and torque input to the motor, steel was selected for the lead screw and nut material. This provides the lowest friction coefficients while remaining cost effective. Also, the pinion size was increased, which decreased the amount of angular rotation of the crank arm. This decreased the speed at which the lead screw had to rotate, which lowered the power.
Due to the calculated factors of safeties, we predicted the first mode of failure is going to be the lead screw.
Our final design came out to a total cost of $4,097.63. All of our calculations, coding scripts, and resources used are linked below.